Yeah, I'm just going to walk you through a little handout with 12.4 to kind of get you started. This problem is a flow problem, so our system boundary is a control volume, or we have flow across the boundary at 2 inlets and flow across the boundary at 1 exit, so it's an open system. And I've got hydrogen in one pipe, oxygen in another, and then hydrogen, oxygen mixed in the outgoing stream. I'm told the mass flow rate of the hydrogen, the oxygen coming in. Of course, the mass flow rate, total mass flow rate coming out is the sum of those two. So m dot 3 equals the m dot of the oxygen plus the m dot of the hydrogen. But we kind of do the problem as treating the hydrogen and oxygen in the exit separately. And we're trying to find the temperature of this mixed stream. Now, something to note is that the mole fraction of the gas coming in is 1. So in state 1 here, the mole fraction of hydrogen is 1. It's all hydrogen. And the mole fraction of O2, oxygen, in this pipe 2 is 1. But when those flows come out, the mole fraction of hydrogen is not 1. It's less than 1. So they're shared. The sum of the two mole fractions, hydrogen and oxygen, equals 1. So here at state 3, I would calculate the mole fraction of hydrogen as the molar flow rate of H2 over the molar flow rate of H2 and O2. So that's how I'm going to find the mole fraction at the exit. Alright, so we're given the mass flow rates, and we need to find the molar flow rate. So that's the first thing we do. So wrong value entered here. But so if we know like we did before, if we know the molecular weight, we can divide the mass by the molecular weight and get the moles. If we have a mass flow rate and we divide by the molecular weight, we'll get the molar flow rate. So we just take this value divided by the molecular weight for H2, which is 2.016, and we'll get the molar flow rate. So this would be 0.2 divided by 2.016, and then molar flow rate of oxygen, 0.3 divided by 32. Then the molecular weight for the mixture would be the total mass, which is 0.2 plus 0.3 divided by the total moles, which is this number and this number. Now they're rates, so we're adding not the mass and the moles, but the mass flow rate and the mole flow rate. But the fact that we're doing both numerator and denominators rates cancels that out, that it's on a per rate basis. We just need to be careful that if this is kilograms per second, then it has to be kilomoles per second, so that we have the same time in the numerator and denominator. So this is just going to be m dot total over n dot total. So in other words, m1 plus m2, of course those are dots, I can't put that on here, and then n1 plus n2, and 1 dot plus n2 dot. Right? 1 and 2 being oxygen and nitrogen, not state 1 and state 2 really. But okay, then determine the constant pressure specific heat. So that's just looking up something in the table. So we go to the tables, and in your book should be table 820, and if you go to oxygen, and at 300 degrees you'll find specific heat, and should be 0.918 for oxygen, and then 14.307 for hydrogen at 300 degrees. So those just come from the tables. Table 820. Same thing for this. T3 is a little more difficult, so let's look at what we're doing here. So we need to do two things. We need to write out the first law for our system, and assuming it's steady state, it's an insulated, so where it says insulated mixing valve, so it's no heat transfer, no work, there's no moving boundaries. Sum of all the mass flows in times enthalpy in minus the sum of all the mass flows out minus times the enthalpy out, neglecting changes in kinetic and potential energy. So I end up with m dot of the H2 times the enthalpy of the H2 at state 1 or at pipe 1, and m dot of the O2 times enthalpy of the O2 in pipe 2. And then at the exit I have both a flow of hydrogen and a flow of oxygen, so I'm going to have two terms there, even though there's only one exit. I'm looking at the mass flow of the hydrogen, the mass flow of the oxygen in that exit pipe. For constant specific heats then, H can be written as CPT, although the specific heat is for whatever gas is flowing. So I have H as CPT with the specific heat of hydrogen for pipe 1, the specific heat of oxygen for pipe 2, of course with the corresponding mass flow rate. And then for the exit, same thing, it's at T3, both of them, but the mass flow rate of H2 times Cp of H2. So I end up with T3 in both these terms, so I can factor out T3 and then divide by this plus this term, which is the denominator here, and I end up then with one equation, one unknown, solve for T3. So first law, basically. All right, the finding the rate of entropy reduction is a little more involved. So we already found the specific heats here, and Y primes discussed that, but anyway, you can pause the video here and look at what I mentioned. All right, then the second law to find entropy reduction. I read out the second law. The problem is assumed to be steady state. There's no heat transfer, so I'm left with summation m dot ISI minus summation m dot ESE equals the rate of entropy production. So I'm going to solve for rate of entropy production, and I get at the exit the mass flow rate of the O2 times the entropy of the O2 at state 3, and then same thing at state 3 for the hydrogen, minus then the mass flow rate times the entropy of the O2 at pipe 2 and the mass flow rate of the hydrogen in pipe 1 times the entropy of hydrogen. When I kind of rearrange this with mass flow rates, kind of separate out the common terms, do all the oxygen together and all the hydrogen together, I have a delta S times m dot and a delta S times m dot. The delta S's, I can use the equation for delta S either on a mass basis or a mole basis. I went ahead and did it on a mass basis here. So I have the specific heat per unit mass. And then since it's constant specific heats, I'm not using the tables, so there's an equation for that. Cp natural log of T exit over T inlet minus R natural log of P exit over P inlet. Now in this case, like always, when I'm doing entropy with the ideal gas mixture, I use the mole fraction times the actual pressure. So this is P3, and this would be whatever pipe I'm referring to. So for the oxygen, it would be pipe 2 pressure, and for the hydrogen, it's pipe 1 pressure. But in this problem, all the pressures are the same. So this P exit over P inlet for both the oxygen and the hydrogen is going to cancel. Same pressure in all three pipes. The pressure is the same in 325 kPa here and here, and then when it comes together, it's still at 325 kPa. There's no pressure drop, in other words. So those cancel, but what doesn't cancel is that at the inlet, the mole fraction is 1, but at the exit, it's not equal to 1. So we use the mole fraction of the oxygen as the exit, and so we just get the mole fraction of oxygen at the exit, and for this equation, the mole fraction of hydrogen at the exit. So this is my delta S for O2, my delta S for H2. I put those in, multiply them times the mass flow rates of each oxygen and nitrogen, or hydrogen and oxygen, add it together, and I get the entropy generation. So not a lot of questions here, but a fairly involved equation at the end with a lot of terms if you string it all together. We haven't done as much with entropy generation in Thermo 2, so this is a good question for you to kind of refresh your memory a little bit on entropy change, entropy generation using the equations. I hope that helps.